afternoon and welcome to AI Bytes, session 5, which is neural networks. Thanks to those of you watching at home or from your desk or wherever you're also watching when you watch on YouTube. Today, we're going to have a session where we're going to start out with a little bit of refresher on generative AI, which leads into neural networks. We're going to give you some terms so that you're familiar with some of the terms in neural networks. And Eve is going to be doing that. And then we're going to go on to interviewing and hearing from some IMSA.ai students working on AI machine learning projects. We're going to tune in at their SIRs during lunch hour, as well as I think we've got one coming here. So we're going to try that via Zoom and in person and see how that goes. If there is time, we do have a neural network simulator. I don't know whether we'll have time, but we can always send out the link for that afterwards. So if you want to practice, right? All right, next slide. So generative AI, you want to take it away? Okay, here's Neve.
So generative AI is, what we've been discussing for the past however many weeks, and it's basically a computer program that can generate original content. And there are a variety of generative AI programs that we use relatively day to day. ChatGPT, Big AI, things like that. So the way that they work is generative AI is built on a program called a neural network. So what a neural network does is it takes information and then it processes that information to predict an ideal outcome. So we can go over a few key terms for neural networks. So neurons. So a neuron is a single unit of a neural network. So the way that a neuron works is that a neuron will take two pieces of data and then convert it into a single piece of data. So it's, think sort of like how if I were to give two pieces of input to describing factors of an object. So if I were to say that an object is round and red, the neuron would be able to tell me it's an apple or something similar to that. Neural networks, of course, work on binary data. It's a bit more mathematical than that, but that's, I guess, the high level concept of it. So then layers are sets of neurons. So there's an input layer where information is inputted into the neural network. There are the hidden layers where this information is processed, and then there's the output layer, which is the information that, or the prediction that is created by the neural network. So then, the way that neurons work is that they assign each of the two inputs different weights. And by assigning it a weight, it can determine the importance of that factor in the overall prediction. And an epoch is the number of times that the neural network is trained or tested by giving it input, and then getting the output, and then modifying the weights of the neural network based on whether that output conforms to what you want it to look like. So I know this is really confusing, but we'll do a demonstration. So a couple more key terms. So test loss and training loss are the errors that you see when you run a neural network. So after an epoch, the training loss is however different your output is from what you want it to be. And the test loss is the same, but when you're testing it, when it's not working on predetermined data. So then there's also noise. So noise is extraneous data, which is not conformed to the overall pattern or has significant error to the point where it's inconsequential to the neural network. And the batch size is just the number of samples that you can process in one epoch of testing. So how do neural networks work? So we can do a quick demonstration. So say we are trying to figure out a neural network to determine what the temperature is when depending on how many times a cricket chirps per second. So according to the USDA, that relationship is something like 15x plus 37. So now that we have that relationship, we can use a neural network to determine that, to discover that by giving it a data set. So take, for example, two inputs. So in the input layer, we have x1 we will only have one hidden layer with a single neuron. And then we have the output. So the way the neural network works is it takes data from, say we have this as a scatter plot, where there's a bunch of data points. And for example, let's take the data point 0, 37. So the way it'll work is it'll input that with a set of weights, say for example 0.5 and 0.5. So when the x value is 0, 0 times 0.5 is 0, and 1 times 0.5 is just 0.5. So the output would be 0.5. So that is not near 37, and 37 is what we want this value to be. So the way it'll work is it changes, it adjusts the weights. So now this is one epoch, and then it'll go back, and now for the next epoch, it'll adjust the weights to something a lot bigger. So say we adjust it to 37. So then 0 times 37 is 0, and then 1 times 37 is 37. So, yay, it works now, except it only works for this singular data point. So that's why the machine learning algorithm will refine its data by training on every single one of these points, or how many are in the batch size, which is one of the key terms we talked about on the last slide. And it'll be able to refine its model until it's able to accurately predict the temperature based on the number of times that the cricket chirps. So say for example, it picks the next data point 1, comma. So with this model that I created off the first data point, this won't work because what you get is 37 plus 37, which is 74. So 74 is not equal to 52. So then it would have to refine its model and have to refine its data. And then eventually, it would be able to come up with a prediction that is relatively accurate based off of this data set. And the way that we determine this, the way that we quantify this is loss, which was another one of the key terms that we talked about last time. So the difference between, say, 74 and 52 would be the training loss, while when we were to test this neural network in a different setting, or something where we don't know the answer, that would be the test loss. And then, so the two things that we just talked about, evaluating the output based on the input, and then going back and changing the weights, that's called propagation. So evaluating the output is called forward propagation, and going back and changing all the weights is called back propagation. And then of course, one time going forward and back is a single epoch. And the more epochs you take to test, the more refined your program will be, and then you'll be able to better predict whatever it is you're trying to predict with neural networks. So really, what a neural network does is it predicts things. It takes an input and it gives you an output based on its analysis of a certain set of data. And at a core level, no one really knows what happens in this stage. We know the inputs and we know the outputs, but the neural network was designed to work like a human brain, which is why it's called neural. And we don't really know, no one knows what happens here, which is why it's really important for computer scientists to study and machine learning and neural networks so you can really understand how they think, because that's still a very unknown part of computer science. Yeah, so I think we should have our student presenter, and let me go check on it. Okay, give me 1 sec. So let me.
Sorry.
Hi. Can you hear me? Yeah, okay.
Top left.
Okay, can you hear me now?
Yeah.
Okay, perfect.
That's why you were going to
Okay, how about this?
Yeah, that's it.
Okay, so, you probably share this with
Yeah, but give me a screen share permission.
I'm gonna get rid of the accordion music.
Okay.
Although I could dance. I'm gonna get rid of the accordion music.
Okay, yeah, so, yeah, if you could, can you share your screen now?
Yeah, I can share screen. So, is that good?
Yes, perfect.
Okay. Cool. Am I good to start?
Yes.
Alright, cool. So, hey everyone, this is my MSI proposal along with another student, Ankit Shetty. He is not here today, but I am going to present on behalf of both of us. And this is our MSI project. It's called Class IQ, and basically, we like to call it a module essentially for IMSA to use and IMSA students in general. Basically, there is a feature we call Educational Resource Management, which we acronymed ERM. And what we'll do with this is we'll have a multimedia resource. We'll basically be providing multimedia resources for students and teachers to use. And basically, it'll run through a search engine like algorithm. So imagine you have a website or a downloadable which features a obviously aesthetically appealing user interface, and then also has a search engine, kind of like a search bar type thing. And what you do is you request for something related to maybe something you're studying, for example. Let's say you're studying AP Calculus, right? And you want to maybe find some resources, because it is hard to do this when you're searching on the internet just regularly, and especially when many students have a tendency to do better with things like videos as opposed to just regular articles or links and stuff that would provide them with just an explanation and a couple of problems, right? So with this module, what we're going to do is basically give the students their resources and also target them with like only IMSA materials. So that means we are using the IMSA database, which is actually available on the library, and then also going to partner with some of the classes. For example, we definitely aim to get in touch with the science department, which is and we're going to start with advanced biological systems in that as a class, and then also going to get in touch with the math department and start going through some of the calculus. And what we can do with this essentially is we'll get a whole set of data, including worksheets, maybe recommended videos that they have, as well as classroom material in general, that will allow students to stay ahead of the course and know what they're and then be ready for when they take the course, or if they're already in the course, then they'll be at the right pace and make sure that they're successful. So we'll do this through web scraping technology to analyze all the data and organize it. And currently we're using Scrapy to do so. However, we also plan on implementing a LLM algorithm just to make sure that the internet data we collect is already as organized as the Scrapy data. So ideally, we want to do it with two different methods. One for the IMSA database, which will be through scraping, and one for the internet, which will be through the LLM. And then lastly, we have the NLP-based content recommendation engine, which is basically how the search engine will function, right? So it'll be paired with an ML algorithm, which optimizes based on user input and individual search queries. So that way, when you're it can filter through the entire database that we save, and then we will be able to essentially provide them with the exact multimedia they're looking for. So yeah.
Thank you so much. Yeah, I think that's awesome. Thank you so much for coming. So now we have another.
Alright, hi everyone, I'm Sridhar, and I'm also working with Soham Kashyap, who's not here today, for the stock portfolio optimization. Okay, so we're basically making an algorithm using AI that is going to create a stock portfolio that's optimized for the least amount of risk for the greatest amount of profit potential. So here's kind of like the workflow of our algorithm. So first, on the website, the user is going to input a list of stocks that he wants to optimize for. Then from the website, which is like the front end, this is where the user is going to interact with our algorithm. All of that, the list of stocks is going to be sent to the back end. So this is our first stage of AI, which is using web scraping and LLM. So the web scraping and LLM takes the list of stocks, searches the web for like news articles or updates on those stocks, and then sends that to a language processing model, which kind of converts it into like a number, like a rating of the stock based on like the news. And then the XGBoost algorithm uses a technique called extreme gradient boosting to predict the prices of stocks based off of like historical data. Then all of that data is going to be sent to the next model, which is mean variance optimization. This is kind of just another like AI tool that will take all of that data and optimize it for the least amount of risk with the greatest amount of profit. And that's going to create a weighted portfolio, which tells the user how much percent he should invest in each stock, and then that's just finally going to be returned to the website. So some tools we're using GitHub and GitHub to store all of our all of our code. We're using the Y-Finance API to get like the historical price data. We're using the XGBoost Python package for the XGBoost model, and then we're using beautiful soup web scraping to get the. That's all. Any questions?
Do you have any ideas or plans on what you could do with the tool once it's live, or how you could provide feedback? Like, how are you going to know if people are using it, or what they're using it for, or?
So we're going to post the website live, and then we can use search engine statistics to see how many people are using it. And then it's also going to be connected to our backend, so we'll kind of get like the data that they put into the website. So we'll see how many people are using it.
You said that a lot of it's driven by web scraping and searching news articles for particular stocks. Say I'm a bad actor in the finance industry and I decide I want to badmouth the company to trick this algorithm, so I'm going to put out a bunch of news articles that basically talk bad about the company in order to try to find the company. Are you guys weighing that against other sources to kind of offset those kind of manipulations? Because I would imagine just based on that, that'd be very easy.
Right, it would be. So we're trying to get like as much data as we can, so that will help minimize it. And then we're also combining it with the XGBoost algorithm and the mean variance optimization as well to like weight it differently. So it has it's evenly split between the two.
Okay, thank you so much. So we have one more presentation. If you'd like to.
Hey guys, I'm Jaron. Our research project is in 3D graphics. So the current method of 3D graphics, as some of you may know, is called polygon meshing. If you've worked in Blender maybe. We hope to optimize this model to provide faster results basically. And so everything that relies on 3D models, so 3D assets, video games, animated movies, they rely on 3D meshing. And this is a process that graphics cards are highly optimized for. So they're essentially very optimized to perform triangle calculations. That's what they are at the lowest level. And we're hoping to optimize this. So hierarchical data structures are essentially, you can think of it as a tree where you have a root, and then you have branches, and then on those branches you have leaves. Yeah, sure. So essentially we have a base structure, and from there we can branch off and create smaller structures. And right now this may not look like much, but if I were to draw a cube, this represents an area of 3D space. We can subdivide this into 8 cubes by splitting it in half 3 times. So not exactly very good at drawing, but I can try. Yeah. 8 cubes. There's 8 cubes in here. You'll have to take my word for it. And that can be represented as one overlying structure for the 8 cubes, and then 8 children that are each individual. This is actually, it turns out, a very efficient way of modeling this. And we're using this for speedups. There's a set of functions called spherical harmonic functions, which actually show up in quantum mechanics. And they basically represent a set of values defined over a sphere. So you can think of, if you have a sphere, you'll have a particular value at every point along the sphere. So maybe it's like this much over here. I'm representing it as a vector, but you can think of it as like 5 over here, then maybe like 2 over here. And these allow us to present different values depending on which way you're looking at the sphere. And on each vertex on this cube, so on each subcube, you can think of this as one of the smaller cubes within the larger structure. Each vertex, so you'll have 8 of them, has a spherical harmonic value. And that we combine these spherical values in a mathematical way that I don't want to get into. But we can use that to generate a color value for each cube inside this hierarchical structure. And this presents the opportunity to increase the speed of the rendering process. And we hope to use this to leverage this to create viable 3D scans of objects. So we can go from 2D pictures to 3D models. If we were to scan in, this marker, we can take pictures of this marker from various angles, and we would be able to reconstruct it into a 3D model. And it would be able to go from pictures to a 3D model that's on your screen in minutes rather than hours or even days, as proposed by previous methods.
Anybody have any questions before you leave? Okay. Do you want to briefly just talk about your skin cancer detection app?
I don't think that's me.
Oh, that's not. Okay, yes, sorry. Okay. I was thinking it was you. Okay. We have another student that has developed a skin cancer testing app. I was thinking it was him. It's not. We've got more. We have a lot of different students working. So he's part of IMSA.ai. IMSA.ai, there are about, 30 students in IMSA.ai, roughly, and 3 teams. And they have 3 different projects at 3 kind of different levels, and they are working at this at their own pace, and you can see that there are different levels of complexity. This one is the highest level, correct? Right, obviously. So, if you want to know more about IMSA.ai, you just come down to Into. It's an Into group, and Steve Goldblatt here at IMSA is in charge of that. All right, what's next, Neve?
A little advertisement for next session, which is going to be in a while. It's going to be in second semester at the end of January, so January 31st. We will be having our session, which is AI tools to enrich education. So this is the second time around with AI schools. We're using some new ones, some ones that we hope to pilot here at IMSA. It's going to be very exciting, so we really love to see you there. So now, since we do have some time, we'd love to experiment with a neural network simulator and a little bit about how neural networks can be applied, not just in AI like ChatGPT, but in a variety of different forms by which we can create, by which we can see that there's neural networks are everywhere. We see neural networks everywhere from cars, GPS detection systems for like, oh, there's a car next to you. I mean, Tesla's using this in their self-driving cars. This is actually used a lot in medicine with data analysis. And specifically, deep learning is actually a really great, has really great potential for machine learning and artificial intelligence, just because there are a lot of ways to apply this. So, a little bit about applications. We have a short video for y'all. So while you watch, please consider how do these neural network applications, how are they reflective of the neural network's purpose in itself, as well as how does this work with generative AI? So how can these neural networks be applied in something like ChatGPT, something that we've seen before?
Today, artificial intelligence helps doctors diagnose patients, pilots fly commercial aircraft, and city planners predict traffic. But no matter what these AIs are doing, the computer scientists who designed them likely don't know exactly how they're doing it. This is because artificial intelligence is often self-taught, working off a simple set of instructions to create a unique array of rules and strategies. So how exactly does a machine learn? There are many different ways to build self-teaching programs, but they all rely on the 3 basic types of machine learning: unsupervised learning, supervised learning, and reinforcement learning. To see these in action, let's imagine researchers are trying to pull information from a set of medical data containing thousands of patient profiles. First up, unsupervised learning. This approach would be ideal for analyzing all the profiles to find general similarities and useful patterns. Maybe certain patients have similar disease presentations, or perhaps a treatment produces specific sets of side effects. This broad pattern-seeking approach can be used to identify similarities between patient profiles and find emerging patterns, all without human guidance. But let's imagine doctors are looking for something more specific. These physicians want to create an algorithm for diagnosing a particular condition. They begin by collecting 2 sets of data: medical images and test results from both healthy patients and those diagnosed with the condition. Then, they input this data into a program designed to identify features shared by the sick patients, but not the healthy patients. Based on how frequently it sees certain features, the program will assign values to those features' diagnostic significance, generating an algorithm for diagnosing future patients. However, unlike unsupervised learning, doctors and computer scientists have an active role in what happens next. Doctors will make the final diagnosis and check the accuracy of the algorithm's prediction. Then computer scientists can use the updated data sets to adjust the program's parameters and improve its accuracy. This hands-on approach is called supervised learning. Now let's say these doctors want to design another algorithm to recommend treatment plans. Since these plans will be implemented in stages, and they may change depending on each individual's response to treatment, the doctors decide to use reinforcement learning. This program uses an iterative approach to gather feedback about which medications, dosages, and treatments are most effective. Then it compares that data against each patient's profile to create their unique optimal treatment plan. As the treatments progress and the program receives more feedback, it can constantly update the plan for each patient. None of these three techniques are inherently smarter than any other. While some require more or less human intervention, they all have their own strengths and weaknesses, which make them best suited for certain tasks. However, by using them together, researchers can build complex AI systems where individual programs can supervise and teach each other. For example, when our unsupervised learning program finds groups of patients that are similar, it could send that data to a connected supervised learning program. That program could then incorporate this information into its predictions. Or perhaps dozens of reinforcement learning programs might simulate potential patient outcomes to collect feedback about different treatment plans. There are numerous ways to create these machine learning systems, and perhaps the most promising models are those that mimic the relationship between neurons in the brain. These artificial neural networks can use millions of connections to tackle difficult tasks like image recognition, speech recognition, and even language translation. However, the more self-directed these models become, the harder it is for computer scientists to determine how these self-taught algorithms arrive at their solution. Researchers are already looking at ways to make machine learning more transparent. But as AI becomes more involved in our everyday lives, these enigmatic decisions have increasingly large impacts on our work, health, and safety. So as machines continue learning to investigate, negotiate, and communicate, we must also consider how to teach them to teach each other to operate ethically. Today,
Okay, so that video sort of went over the different ways that AI can be applied and how the effect of supervisors or researchers within that machine learning process can develop an AI's response, and how AI can be utilized in different ways in tandem with individuals in order to best predict whatever outcome you're trying to predict. So that application was for medicine and for patient diagnostic. Do any of you have any ideas on what other applications AI can be used for and how machine learning sort of is present in a variety of fields?
I mean, possibilities are endless, for sure, in my opinion. I think it's interesting. I don't like the idea of machine having to learn like human death, and you know what I mean? Like, I'm sure there's many parameters to mitigate that, but I also feel like there's going to be a process where like AI is going to have to learn. Like, when it comes to medicine, what works if it doesn't work, and new kind of drop periods or new stuff that's going to happen, which is interesting.
Yeah, I mean, I guess that's also important to recognize that AI is trained on data that we give it. So there's always going to be some sort of inherent bias within that AI, and understanding and mitigating that bias is a really important part of the field that we now call AI ethics, which is something that we're hopefully going to be discussing in another session, which you all should definitely come to. Another thing that we want to talk about, how do you think this approach to AI, this idea of being given a data set, learning on this data set, and then being able to apply that, how do you think that affects the way that ChatGPT or big AI works? Because we know like large language models are just neural networks applied on these incredibly huge data sets of really just information. And so how do we think we can apply that? So how do you think we can use ChatGPT more effectively knowing this? What data sets would we give ChatGPT in order to, for ChatGPT to learn on? Because ChatGPT can be trained. There is a training model for ChatGPT where you sort of get a blank program and you give the data that it can train on. So how would any of y'all use that on the day-to-day lives?
Well, the example of the first IMSA AI team, right? They're going to feed it all the IMSA information, right? And from different subsets of information to be able to be IMSA-like. Maybe it could be policy, it could be student focused, or it could be classroom focused. There'll be a lot of different ways to make that the IMSA AI.
And the second presentation too, with providing the stock portfolios and
Yes.
historical data and how that can be applied. But then it's also important to understand that with like that example with stock, the student was using a variety of different algorithms. So there's not just one way to create a neural network. So, I mean, this is the simplest neural network possible with one neuron and one layer. But there's a lot of different algorithms that can be used in order to make neural networks more specific or more creative, which really does reflect how we see neural networks. Just because neural networks in and of themselves are incredibly complex and really, like I said in the video, we don't know how they work. So it's important to be able to sort of utilize it, but also understand that it's not foolproof, which is why there's a bunch of safety concerns with neural networks and things like that. So do any of y'all have anything to comment on about safety concerns or ethical concerns with neural networks and how sort of these potential drawbacks can have an impact on our lives?
You mentioned that there's a little bit of a magic trick to it all that you don't understand. I understand that even like Sam Altman, like the CEO of OpenAI, has said very similar things. Like underneath all of this, there's like something about it that we don't really understand how it's doing what it does. And that's kind of worrisome because it's like, we probably should figure that out before we base our entire society and economy on how this thing works, just my opinion. But it is a little scary, I guess.
Okay, thank you so much. So now we're going to go into a hands-on simulation. So this simulation is called TensorFlow. So if you can open up your laptops, this is completely open source. You don't have to create an account or anything. So it will be playground.tensorflow.org.
Or scan the QR code.
And if you don't have your laptop, we can probably get a laptop station.
It's okay, I'll watch everybody.
Yeah, and we'll open it up on the. Where were you able to get the first one?
It just went, just juice go.
Okay. So this is what the simulation looks like. So there are a lot of parameters that are pretty complex, but let's try to keep it as simple as we can for now. So let's pick the simplest data set. Can we pick the linear data set? Or like, okay. So this data set is pretty simple, where if a neural network is inputted a negative value, the value should be negative, and if it's inputted a positive value, the output value should be positive. So this is quite possibly one of the simplest data sets there is. And so now let's play around with some of the parameters. So let's, how about we only make it one hidden layer and 2 neurons. And our input should be just x1 and x2. Yeah, okay. So as you can see, this is more of a graphical view of how it's changed. So, so what we want is something that looks like this. So this is the data set that we were given. So it's here, here, which should essentially, the sort of, I guess if you would view this as like abstract, it should look like this. This is what we want it to look like. We want here it's orange and here it's blue. So as you can see, the neural network does a pretty good job at that, actually. Just because it's able to take a vertical line and a horizontal line, and it's able to connect these and sort of, I guess, superimpose them onto each other and make it a diagonal line. So that's sort of the more abstract interpretation of it. So if you want to look at the weights, can we take a look at the weights possibly? So the weights here are pretty similar. So like 0.4, 0.33, here it's 0.47, 0.27. So really, that just says whether, like which model is more diagnostically significant in understanding how this input relates to the output. So I guess where you can really see it numerically is with loss. So when you start running the program, you can see that the loss is 0, which means that this is actually a perfect model because it's just a simple diagonal line. So you'd expect it to be perfect, and it is. There's absolutely 0 loss. But what you will notice is when we start testing, the loss is actually pretty high. It starts off at around 0.1-ish. I don't know if y'all can see that, but the loss starts off pretty high when we're at about like 100 epochs or so. But when we get more and more epochs, when we're running the program more and more, once we get to around 200, 300, then we can see that this is just perfect. This is a perfect model. So that just goes to show that the more you test a program, the more effective it'll be. So now let's take a look at a bit more complex data set. So this is very hard to see. Okay, this data set is a bit more complex because here, the kind of shape that we're looking for is a little like blob. That's what we want to see. And if we're only given 2 straight lines, it's very difficult to make something blobby with 2 straight lines. So, can we run this program? So as you can see, there's a pretty high loss because the 2 lines, they're only able to come up with something like this. Because when we're working with straight lines, it's not exactly an ideal way to run this program. So now, let's try some more creative inputs. So if we had, say, or actually try it again. Yeah, okay. So this one looks a bit more promising because when you multiply the 2 inputs together, as you can see, there is a bit more of a distinction there that seems pretty promising. So let's try running this program. Okay, that's a lot better. It went from 0.2 to 0.003. So that's just another way that neural networks are able to comprehend this information in a sort of more abstract way, just because now it's more easier to digest when you're looking at shapes as opposed to numbers. So let's just try one more example. So can we try the spirally one? Yes, okay, so this one is quite possibly the most difficult of them all. Because the shape that we're looking for now is like something like this, which isn't the easiest for a neural network to work with. I mean, when you only have straight lines, so let's start with just 2 straight lines. When you just have 2 straight lines, can you run that? That is a pretty high loss. That means it's wrong about half the time, which isn't ideal for a neural network program. I mean, if this was like in your self-driving car, I wouldn't be very reassured if it was wrong half the time. But so, I mean, the closest it can get is like a triangular thing. I'm not completely sure. Now let's try with as many various inputs as possible. So let's try all of them. And since we want our data to be a little bit more precise, let's have more hidden layers, more neurons. Okay, let's try this. Okay, okay, it's getting better. It's definitely getting better. Okay, so like 0.3. Very interesting. Yeah, so even with all of these neurons, it isn't able to come up with a definitive idea for what this looks like. Just because our inputs aren't that great. We're only given a bunch of straight lines. And when you're trying to create a little spirally thing out of a bunch of straight lines, that's pretty difficult. And as you can see, there's like these little spikes. And that occurs because this is a real neural network that's actually being trained in real life. And the way that that works is sometimes you get lucky and it's right most of the time. And other times you get really unlucky and it's wrong a lot. But yeah, see, like it's getting there. It's definitely getting there. It's like 0.2. Maybe after about like 100,000 epochs, we might be something close to a spirally thing. But yeah, not exactly the most promising program. So that also, I guess, goes to show that neural networks are only as good as the input you give it. And the output that you can get is also only as good as the input you give it. So even though we don't understand what's going on in the middle, we know how our inputs affect our output. So even though there's a lot of ambiguity, we need to, when we give a neural network an input, we need to sort of understand how that's able to create the output. So, I mean, I can tell you that these two lines can be combined and get like a diagonal line. I don't really know how this neural network is doing it. I don't know what goes on within its head, but I do understand how what I give it can affect its loss, how correct it is, what it does. Okay, like it's like pretty good now. Like it looks like sort of a spiral. It's like kind of right. Let's try some more neurons. Maybe some more layers. Okay, so it got lower a lot faster. And that looks pretty good. That looks really good. So once again, more neurons, more layers, you're able to get more accuracy. And that means that every time you test it, you're able to get more feedback. And you're able to, when you do back propagation, you're able to change more weights to become more specific. You're able to lessen the error by lessening your margins that you have just because there's so many neurons. And you can also see with all the little connections, the web, those are the weights. So the thicker ones are the ones that matter most, while the thinner ones matter significantly less. So, I mean, this looks pretty good. Well, it's definitely not perfect, and you can see where these constraints are coming from. The way that these shapes are sort of, they're a single shape as opposed to multiple shapes, which would be ideal. But there's still a lot of ambiguity here, and there's still a significant amount of error, like half of like about 5% error, which isn't ideal, but I mean, it's a lot better than 40% error. So it's very interesting to see. So yeah, do any of y'all have any thoughts on how this neural network works?
The more sources you have from different areas, the more accurate you're going to be getting, right? Depending on where the sources come from.
And I mean, you can also see how the outputs of the neurons are changing. So like, in the first layer, the neurons are pretty inaccurate. Second layer, you're seeing a little bit, there's this formation of the shapes. But in the third layer, that's where things really start to look sort of like spirally things. You can see how the neurons that look most like spirally things have the largest weights because those are the ones that are most accurate. So like in the second layer, the bottom one and the one right above it, so the second to last and the last one, are both they look pretty spirally and they have the highest weights. And that top one, the product of those two looks even more spiral. And the product of that one and the product of that one and some other third layer ones makes it look even more spiral. So you can see how these neurons are able to take this data and sort of develop original ideas from it. If we try to run it again, can we run it one more time? It'll be different here than before. Neural networks are constantly changing, constantly evolving, and there is this element of randomness within them, and we don't know where that comes from. We don't know where anything comes from with this neural network. All we know is what we give it and what it gives us. So yeah, feel free to play around with it.
Kind of like our very first, was it our first or second session when we did we had to draw something? And each of us had something different on our screen. It wasn't the same image drawn for everybody. And that was the first aha about the fact that it creates original, right? original content, original images or ideas or answers.
Okay, yeah, so we're just gonna finish off with a short discussion on, so how do you think this, so now we've seen what a neural network does. How do you think ChatGPT does what it does? Do you guys have any hypotheses on how ChatGPT is able to take information and sort of make it an original response?
On data sets.
Yeah, I mean, the more data you have, the better it is.
But how does it know what is garbage data?
It doesn't.
So that's the question.
That's where the problem of ethics, the problem of like hallucinations,
Yes.
where it tells you the wrong things because it doesn't have a second algorithm to filter out the garbage data. It takes every possible way.
Right.
And as you saw,
Yes, yes.
One man's garbage is one man's treasure.
Yes.
They say, so.
Yeah.
I mean, there's also like, as you saw there, in the graph of the loss, it was relatively downward, but there were sometimes it spiked, the loss spiked. It was sometimes it was very, very wrong in one epoch, and then the next epoch was very, very accurate. So there is this element of randomness. That sort of has, when you use a program like ChatGPT, you have to take it, everything that says with a grain of salt, because you don't really know how it works. And then, last slide, please. So yeah, what did you learn and what do you want to see in the future? So our next topic is going to potentially be AI tools. Is there anything else y'all would want to see or this or this?
Whatever you guys decide. Whatever you guys want to give us, you know?
I definitely want to talk to that. I think it's what mentioned that it's going to come down on. I definitely think that's super important. This was pretty cool, like very high level, like obviously neural networks. Pretty interesting. I can't say that I followed 100%, but that's not your guys' fault. That's my fault. This is very, very interesting.
Yeah, I agree. I didn't follow, but just taking it in is really useful and you get little bits. I would like to hear about all the students' AI projects. And then also I thought of something. Did they ever meet in person, all the students in the AI group, or is it all online? Because there's a grant that like, if anyone's interested in like really, do you know what I mean? Not just doing their project for school, but if they're interested in like going with it, running with it, I'd like to tell them about a grant or two that I've come across.
Thank you so much. We really appreciate your engagement, and we'd love to see you at our next session, January 31st, AI Tools.
Thank you.